On May 10th, 2026, a telescope in the mountains outside Tucson, Arizona, spotted a faint point of light moving against the background stars, something nobody had ever seen before. 8 days later, that same object skimmed past Earth closer than the Moon, close enough that if its orbit had been angled even slightly differently, it would have been front-page news for reasons far more serious than a science headline. It wasn't discovered years in advance the way the most dangerous asteroids ideally should be. It was found with barely a week's notice, by a survey telescope doing exactly what it was built to do, and its story says something genuinely important about a gap in humanity's ability to see what's coming, one that has nothing to do with alien objects or invented mysteries, and everything to do with the actual current limits of planetary defense. This is the story of asteroid 2026 JH2, the asteroid that passed closer to Earth than almost anything discovered in recent memory, and what its short, 8-day journey from discovery to closest approach reveals about how prepared we actually are for the next one. To understand why this particular flyby mattered, and why scientists paid close attention to it despite it posing zero actual risk, you first need to understand how asteroid tracking actually works, and why some objects manage to sneak up on even the best equipped observatories on Earth. Every day, according to NASA's own tracking estimates, roughly 100 tons of material falls onto Earth from space. The overwhelming majority of it is dust and tiny fragments, burning up harmlessly in the atmosphere long before reaching the ground. But scattered among that constant, gentle rain of debris are considerably larger objects, asteroids ranging from a few meters to several kilometers across, following their own independent orbits around the Sun, some of which happen to cross paths with Earth's own orbit. NASA and international partner agencies maintain a continuous effort to catalog these objects, known as near-Earth objects, or NEOs, through a combination of ground-based survey telescopes and coordinated tracking networks. As of 2026, more than 37,000 such objects have been identified and cataloged, with over 2,300 classified as potentially hazardous, meaning they're both large enough and pass close enough to Earth's orbit to warrant sustained, careful monitoring. That sounds like a comprehensive system, and in many respects it is, but it has a specific, well-understood blind spot, one that 2026 JH2 illustrates clearly. Survey telescopes generally spot approaching objects by observing sunlight reflecting off their surface against the dark background of space, which works well for asteroids approaching from angles where they're clearly visible against the night sky. It works considerably less well for objects approaching from roughly the same direction as the Sun, since intense solar glare can render them essentially invisible to ground-based optical telescopes until they've already swept past, or until they emerge from that glare only shortly before their closest approach. That specific geometric limitation is a big part of why an asteroid the size of 2026 J82 wasn't caught years or even months in advance, the way scientists ideally aim to catch potentially hazardous objects. 2026 JH2 was first spotted by the Mount Lemmon Survey, a facility located in the mountains near Tucson, Arizona, that uses a 60-inch telescope specifically dedicated to hunting for near-Earth objects. Astronomers Grzegorz Dušanovich and Jordi Camarasa are credited with the initial detection made on May 10, 2026. Once an object like this is spotted, the process of confirming and characterizing it moves quickly, and deliberately so. Additional observatories around the world, coordinated through networks including the International Asteroid Warning Network and the Space Mission Planning Advisory Group, immediately begin gathering follow-up observations, allowing astronomers to rapidly refine the object's exact trajectory, size estimate, and level of risk. Within just 2 days, on May 12th, the Minor Planet Center had gathered enough independent confirming observations to formally announce the discovery and assign it the provisional designation 2026 JH2. That rapid confirmation process revealed several important details. Based on how much sunlight the object reflected, astronomers at NASA's Jet Propulsion Laboratory estimated its size at somewhere between 15 and 35 meters across, roughly comparable in scale to a basketball court, or, in the more visceral comparison several outlets settled on, roughly the size of a blue whale, Earth's largest living animal. It was classified as an Apollo-type asteroid, a category defined specifically as objects whose orbits cross Earth's own path around the Sun, following an elliptical orbit that carries it from just inside Earth's own orbital distance out to nearly the distance of Jupiter, completing a full loop around the Sun roughly once every 7 years. Its closest approach to Earth arrived on schedule on May 18, 2026, at approximately 9:23 p.m. UTC. According to precise tracking data from NASA's Jet Propulsion Laboratory, 2026 JH2 passed by Earth at a distance of roughly 91,572 kilometers, a little under 57,000 miles. To put that in perspective, that's less than a quarter of the average distance between Earth and the Moon, though still comfortably beyond the ring of geostationary satellites that orbit roughly 36,000 kilometers up, providing services like telecommunications and weather forecasting. During its closest approach, the asteroid brightened to an apparent magnitude of roughly 11. 5, faint by naked eye standards, but bright enough to be observed directly through a modest backyard telescope, which is exactly what a number of amateur astronomers and organizations, including the Virtual Telescope Project, did, tracking and broadcasting the flyby live as it happened. Throughout the coverage of this event, scientists were consistently, carefully clear about one central point. 2026, JH2 posed no danger to Earth whatsoever. Richard Binzel, a professor of planetary sciences at the Massachusetts Institute of Technology and the inventor of the Torino scale, the standard tool astronomers use to categorize the potential danger of an asteroid impact, put it about as plainly as it can be put in comments given to CNN following the discovery. 2026 JH2 will pass safely by the Earth. That assessment wasn't hedged or qualified. Once astronomers had gathered enough tracking data to confidently map the asteroid's trajectory, there was no meaningful uncertainty left about whether it would strike Earth. It wouldn't, and the tracking data made that clear well before the actual flyby occurred. So why does an asteroid that never posed any real threat deserve this much careful attention and study? The answer lies less in what 2026 JH2 actually did, and more in what its short 8-day journey from first detection to closest approach reveals about the current state of planetary defense as a whole. Juan Luis Cano, an astronomer with the European Space Agency's Planetary Defense Office, offered a useful, grounded perspective on how events like this one tend to get covered in the media and comments given around the time of the flyby. Publications need to have these cliffhangers to have visits, Cano noted, acknowledging candidly that close approaches like 2026 JH2s tend to generate outsized media attention relative to their actual danger, precisely because a dramatic headline draws readers even when the underlying science is comparatively mundane. But on a daily basis, we are visited by many objects, he added, reinforcing the point that objects of this general size pass near Earth with genuine regularity, and the vast majority of them, including this one, pose no risk at all. But Cano's broader point wasn't simply that people shouldn't panic. It was that events like a 2026 JH2's short detection window represent a genuine ongoing challenge for the field of planetary defense, one that deserves serious attention precisely because the next object discovered on a similarly short timeline might not turn out to be quite so harmless. As one detailed analysis of the event put it directly, the real story of 2026 JH2 isn't that it safely missed Earth, something that was essentially guaranteed once its orbit was confirmed. It's that the event quietly exposes how incomplete current planetary detection systems still are for objects in this particular size range, ones large enough to cause real regional damage if they were ever to strike a populated area, but still small enough to frequently evade detection until shortly before a close approach. That concern isn't abstracted or hypothetical. It connects directly to a well-documented historical precedent that came up repeatedly in coverage of the 2026 JH2 flyby, the Chelyabinsk meteor. On February 15, 2013, an asteroid roughly 20 meters across, broadly comparable in size to 2026 JH2, entered Earth's atmosphere undetected and exploded in the sky above Chelyabinsk, Russia, releasing energy equivalent to several hundred kilotons of TNT. The resulting shockwave shattered windows across a wide area, injuring more than 1,000 people, the overwhelming majority from flying glass rather than the blast itself. Crucially, that object was never detected in advance at all. It arrived from a direction close to the sun, exactly the kind of blind spot that makes objects like it especially difficult for ground-based telescopes to catch early. The Chelyabinsk event remains, to this day, the most significant asteroid impact witnessed and documented by modern instrumentation in nearly 120 years, and it serves as a stark, concrete reminder that objects in this specific size class, too small to threaten civilization as a whole, but large enough to cause real, serious, localized damage, represent a genuine, ongoing category of risk that current detection systems still struggle to fully close. It's worth being precise about exactly where the planetary defense field currently stands in addressing that gap, because meaningful, concrete progress genuinely has been made, even if the challenge isn't fully solved. In September of 2022, NASA carried out the double asteroid redirection test known as DART, deliberately crashing a spacecraft directly into a small asteroid moon called Dimorphos, orbiting a larger asteroid named Didymos, specifically to test whether a controlled, deliberate impact could measurably alter an asteroid's orbital path. The test succeeded, meaningfully changing Dimorphos' orbital period around its parent asteroid and demonstrating, for the first time in history, that humanity possesses a real, practical, physically tested method for altering the trajectory of a hazardous asteroid, provided it's identified with sufficient advance warning to actually plan and execute a deflection mission. That last qualifier, sufficient advance warning, is really the crux of the entire issue 2026 JH2 highlights. DART proved that deflection is technically achievable, it did nothing to address the earlier, equally critical half of the planetary defense problem, actually spotting a hazardous object early enough that a deflection mission would even be possible in the first place. An asteroid discovered only 8 days before its closest approach, as 2026 JH2 was, offers nowhere near enough lead time to plan, build, and launch any kind of deflection mission, even if that particular object had turned out to be on a genuine collision course. Recognizing that specific gap, NASA has been developing a dedicated solution, the NEO Surveyor, a space-based infrared telescope specifically designed to address the detection blind spots that ground-based optical surveys like Mount Lemmon inevitably face. Unlike ground-based telescopes, which are limited by atmospheric interference, daylight hours, and the specific glare-related blind spots that delayed detection of objects like 2026 JH2, a space-based infrared telescope can observe in wavelengths and from vantage points that reveal asteroids invisible to optical instruments, including many objects that spend most of their time hidden in the glare of the sun from Earth's perspective. According to NASA's own stated goals for the mission, NEO Surveyor is specifically designed to find roughly 90% of so-called city killer-sized asteroids, objects large enough to cause serious regional devastation if they were ever to strike a populated area, that currently remain effectively hidden from existing ground-based detection networks. There's a useful historical case that illustrates exactly why sustained, patient tracking matters so much, even for objects that initially appear alarming, the asteroid Apophis. When Apophis was first discovered in 2004, its initial trajectory calculations suggested a genuinely worrying possibility that it could strike Earth on one of several potential dates, including 2029, 2036, or 2068, and it was, for a period, considered one of the most potentially hazardous objects ever identified. Continued observation and increasingly precise orbital calculations over the following years steadily ruled out each of those potential impact scenarios, one by one, eventually confirming, with high confidence, that Apophis poses no meaningful risk to Earth for at least the next century. That outcome wasn't luck. It was the direct result of exactly the kind of sustained, careful, repeated tracking effort that planetary defense researchers rely on to transform genuine uncertainty into confident, science-based reassurance. The same basic process, just compressed into a matter of days rather than years, that quickly established with confidence that 2026 JH2 posed no danger either. It's worth stepping back and being genuinely clear-eyed about what all of this actually represents, since honest context matters far more here than manufactured alarm. Nothing about 2026 JH2 was ever remotely close to a threat to Earth. Nothing about the broader pattern of close asteroid approaches happening regularly represents some kind of escalating danger. Objects of this general size pass near Earth on a fairly routine basis. What made 2026 JH2 notable wasn't its danger level, which was essentially zero from the moment its orbit was confirmed, but rather how little advance warning astronomers had before it arrived, and what that short window reveals about a specific, well-understood, and actively being addressed limitation in current detection infrastructure. That's precisely why scientists treated the event as a genuinely valuable opportunity, rather than simply a relief once the object safely passed by. The close approach gave researchers a rare, cost-free chance to gather detailed optical and, where possible, radar data on the object's composition, spin rate, and physical structure, information that under normal circumstances would require an expensive, dedicated spacecraft mission to obtain directly. Every close flyby like this one, whether or not it poses any actual risk, feeds directly back into the broader models and detection systems astronomers rely on, helping refine orbital prediction techniques and improve the overall accuracy of the planetary defense network as a whole. There's something genuinely worth appreciating in how transparently and quickly this entire process actually unfolded, start to finish, over those 8 days in May of 2026. A telescope in Arizona spotted an unfamiliar point of light. Within 2 days, a coordinated international network of observatories had confirmed the object, calculated its orbit with enough precision to rule out any possibility of impact, and made that information publicly available for anyone to check for themselves. Amateur astronomers around the world were able to watch the object pass by in real time, using nothing more than modest backyard telescopes. And throughout the entire process, the scientists directly responsible for tracking the object were consistently, carefully honest about exactly what was and wasn't known, resisting the pull toward manufactured drama even as media coverage around them leaned into exactly that kind of framing. That's really the through line connecting this specific, ordinary, ultimately harmless asteroid flyby to the much larger, genuinely important question of planetary defense as a whole. The danger was never in 2026 JH2 itself. It was in what its short detection window revealed about the broader system currently responsible for watching the sky, a system that has grown remarkably capable over the past few decades, thanks to coordinated international tracking networks, missions like DART proving that deflection is genuinely achievable, and now missions like NEO Surveyor working to close the remaining gaps in early detection, but one that isn't yet fully complete. As the field's own researchers are quick to point out, planetary defense isn't primarily a question of whether humanity possesses the technical capability to deflect a hazardous asteroid, since DART has already demonstrated that it does. It's a question of whether humanity can see that asteroid coming early enough for any of that capability to actually matter. 2026, JH2 is gone now, continuing on its own independent 7-year orbit around the Sun, due to return to Earth's general vicinity again sometime in the coming years, by which point its orbit will be understood with even greater precision than it is today. It never posed a threat, and it never will, based on everything currently known about its trajectory. What it left behind instead was a genuinely useful, real-world stress test of exactly how quickly the global planetary defense network can respond when something unexpected shows up with almost no warning, and a clear, honest reminder that the gap between we can technically stop it, and we can see it coming in time, is still very much a live, actively worked on problem, one that missions currently in development are specifically designed to help close. If you want to follow how NASA's NEO Surveyor mission and the broader planetary defense network continue working to close that detection gap in the years ahead, that effort is very much ongoing right now. Subscribe if you'd like to keep following where it goes.